If P is inversely proportional to R, if my R is really slow, and when I try to take water out of that really small pore, my P is going to be very high. When the pressure or the stress, typically it's a tensile stress, goes very high, what happens to cement paste? It starts to crack, right? Because the stress is very high. So de-drying or freeze drying, you always end up with a possibility of cracking. But the advantage is that you get all the water removed from the pore system, so you completely know that mercury has gone in and you're sure. With regular oven drying for 60-70 degrees, the problem is that you may have really small pores, that mercury typically is much more denser than water, so mercury will displace water when it pushes through. But you might have some points where mercury would not have displaced water, so what's the guarantee that my results is correct? Now here's a compromise. If I have cracked the sample in de-drying, I will have more mercury that will go in, and then I'll say my pore porosity is higher. In this case, I may have less mercury that will go in, and I might say my porosity is lower. That's where your judgment comes in. Remember, everything in engineering is judgment. There's absolutely nothing. If you are a scientist, facts speak, science speak. If you're an engineer, facts and sciences are a tool to strengthen your judgment call. So you will get this, and then you decide what is a more appropriate situation for me. What is a relative error I may have? Maybe 5% error, can I live with it? And if I'm comparing 5 different systems, if I treat all of them the same way, can I now not compare all 5? Right? So then you say that, rather than saying, and this is exactly the point that I'm coming and telling you guys, right? When you typically say that strength is 15% lower, strength is 20% higher, it goes high and comes low, you're not doing any judgment at all there. You're just following your observations, like you do for your results that you get. Use your judgment and say, comparing A and B, here is the difference between A and B. Therefore, this is why something would have happened. That makes it more easy. Okay, any other questions?
Yes,
You have a question? Yes.
Assuming that concrete is a sponge, so when we apply triaxial pressure, the sponge gets contracted in all the directions. So now the pores also gets closed. Suppose there is a small pore, if I apply compression, the pores get closed. So in that case, how to assess that?
Pore closure is a problem, but your basic assumption that concrete is a sponge is not true. Concrete is a sponge when you say that concrete absorbs water.
Yes.
But when you say that, remember, if you have a dry pore, a pore with nothing inside,
yes,
you can have compression pore closure.
yes.
A drop of water inside the pore makes the story completely different.
Yes,
right?
It will not.
Yeah, because now you have hydrostatic pressure, and water is what kind of a fluid?
Incompressible.
Incompressible fluid, right? Our theory says water is an incompressible fluid. So, and then basically if you have gel pores and you're not drying it to 1000 degrees Celsius, so your gel pores, which are typically the smallest pores, will have water in between those layers. Water is incompressible. Mercury will displace the water through just the process of displacing one liquid by the other, not by breaking the pore. So pore closure, while theoretically might be a problem, on a larger specimen that you put in with this real small gel pores won't be a problem.
And as you told that mercury displaces water, is there any outlet to displace water?
Because it is under triaxial state of stress, you really don't get water outside. But again, once you dry this out, remember we are talking about adsorbed water and gel water. Capillary water should have gone when you heat it at 60 or 70 degrees Celsius. All you're talking about is the adsorbed water on the surface and the gel water, which is the gel pores. Now, if you think about your porosity that influences durability, it is not the water in the gel pores that influences your durability. It's not the size of the gel pores that influences your durability. External agents like chlorides and sulfates and moisture transport through the capillary pores and the smaller mesopores. So, if it does not completely replace it or displace water out of gel pores, I don't bother. Displace as much as you can, and that is again the point that you have to have a comparison system and say that compared to an OPC paste, my paste with 20% fly ash shows me X% lower porosity and X% lower pore size. Now you're totally fine because you're comparing with a known standard.
It's a relative measure.
It's relative, and therefore I know my OPC has larger pores, but putting fly ash or putting silica fume has lowered my pore sizes, and I know from common sense that lowering pore sizes will slow down transport, therefore make my concrete more durable. That is why we need engineers to interpret the data, not the guy on the road. You don't give an MIP data to somebody who's standing on the road, right? You give it to an engineer to interpret. Because you know, see, a lot of things, inbuilt knowledge is so very important, right? What you know from experience, from intuition, from learning, and all you're doing is building on it. None of us are starting. I cannot teach MIP to somebody who is in 7th grade or 8th grade. I cannot teach MIP to a software engineer who knows how to code. He has to know something about a material and something about civil engineering. We have our repository of knowledge that we are just adding on to it, right? So that's how you should think of it.
One more small question.
Yeah.
So there are two types of pores. One is interconnected pores, where percolation can happen.
Yes.
One is an isolated pore, just like an air bubble. So we cannot reach that. So is it missed in the MIP, or is it accumulated?
Generally it is missed, but why do I need it? Why do I need it? MIP doesn't tell you anything about the strength. If I don't want to know anything about the strength, why do I care about an isolated pore? Right? Now, an isolated pore, if I talk about this now, I'll take the entire day talking about the pores. Okay? An isolated pore is a myth. Your cement structure is inherently porous. When you say an isolated pore, you're just saying I have a larger pore. But larger pore is connected by a large amount of smaller pores through the network. And water molecule is so small, it can actually go through all these smaller pores and get to a larger pore. That is the principle behind air entrainment when you have freezing and thawing. Because you put in big air bubbles and water can come through the small pores into the big air bubble. So the idea of an isolated pore is a convenience question. It's not a real fact.
Thank you, sir.
Okay, so let's start with hydration product analysis. So the pore structure kind of story is done. We'll do the hydration product analysis. So basically, how much of CH, how much of CSH, how much of ettringite. We'll do X-ray diffraction thermal analysis. That's all we'll do for the time being because these are the easy techniques. Okay. Okay. So, X-ray diffraction, determining crystal structures. Most of you have seen how an X-ray diffractogram will look like. If not, I'll show you a few of those. Just to give you some history, this is the father-son duo who got a Nobel Prize, shared a Nobel Prize in physics in 1915 for using X-rays to determine the crystal structure. William Bragg and Lawrence Bragg. William Bragg in charge of research on the detection and measurement of underwater sounds in connection with submarines. So he was doing 1915. What is the significance of time around 1915, 1916? World War I, right? So they wanted to find out in the UK, and then it was all British at that time. They want to find out if enemy submarines are coming in. So they want to send sound waves through it and detect submarines. So he was William Bragg was in charge of determining and measuring where the submarines are underwater. And he accidentally did some work on X-ray diffraction, got a Nobel Prize. So basically an accidental Nobel Prize, just like that, was doing something for fun and got a Nobel Prize for it, okay? And that's what we also think we should have, but it doesn't happen these days. But a lot of people, if you look at it, right? And this is something that I always used to wonder. It's also an indication of the progress that we have made as a society. Arrhenius, that I told you about yesterday, all he got a Nobel Prize was for the idea that any material, if it has to go down to a lower state of energy, has to overcome an energy barrier. Sounds so simple, right? And if you think that if I have to have two atoms, atoms by themselves are lower state of energy, molecule is even lower, but if they want to react, I have to give heat or some external energy for them to react. So they have to get to a higher energy through that heat and then come back to a lower energy. I have to do no experiments. I just have to write this equation in terms of a theory, come up with a term called activation energy and relate the activation energy to your molar gas constant temperature. If you see chemistry, do you see anything in chemistry without R and T? Everything is PV, is nRT, R and T is there everywhere, right? You relate it to gas constant and temperature. And you, since you know you have to go up and come down, yeah, the energy has to be in exponential form. It kind of makes logic. And he proved it. He did it, got a Nobel Prize. These guys were doing something else and said, if I pass something through an X-ray, I get all these peaks. And if I know what those peaks are, that tell me exactly what the crystal looks like. Another Nobel Prize, right? It was very easy then, apparently. Not anymore. Okay. So, the idea is the idea of diffraction. In physics, you have reflection, refraction, diffraction, you know all of that, right? The simple things that you teach your students. Reflection, refraction, diffraction. So, we are going to use the idea of diffraction. Very, very, very simple. If I have a wave, you know how a wave propagates, right? Think about a simple sine wave. I have a sine wave here, and typically one wave doesn't come alone. You go and watch the beach. Have you ever seen just one wave and then a complete silence? No. Waves come in groups. It keeps going. Sound is a wave. If you believe the sound, the wave theory of sound and wave theory of light, so, sound and light, electromagnetic radiation goes in the form of waves, and they are continuous waves, right? It's not just one wave, right? You have different frequencies, different amplitudes, all of that. So if I have one wave, and all of you know the terms associated with the wave, the crest, the trough, the amplitude, the frequency, all of that. So I have one wave like this, and another wave coming in, and you have so many waves like that. And suppose I have a scattering event. Maybe just say I have a barrier here when I speak. Sound will still go through the barrier. So if I have a barrier here, if sound waves that are going through from here, through the barrier, if the barrier influences those waves in such a way that they come back out at the same position, the crest and the crest, the trough and the trough are exactly at the same locations, you call it constructive interference. Remember that term from your physics class? You are constructively interfering, which means what? The amplitude is going to be doubled when it comes on the other side. Or the same way, some waves through some scattering events can destructively interfere with the crest of this and the trough of this in the same place. What do you get on the other side? Complete silence. You don't hear anything, right? This is a simple idea. If I pass X-rays through it, the same idea. It can constructively and destructively interfere. So, if you take an X-ray of the human body, the X-ray will go through what? How do you see your bones in an X-ray, white or black? Why? Because the denser bone is constructively interfering with the X-ray so that the signal could be reflected. The softer muscles are black because the lot of scattering and the waves are destructively interfered, nothing is coming back. Right? Simple idea. Harder surfaces, or consider bone to be a crystal, muscle to be an amorphous thing. Easy to think of that way. Bone, more ordered, think of it as a crystal. It will constructively interfere. Amorphous part, destructively interfere. So through crystals you will see, through amorphous materials you don't see. That's why you get peaks in X-rays and crystals and kind of flat or simple small bumps in amorphous materials. So that's a simple idea. So now if I take it a little further, so assume that I have a lattice of atoms which are spaced at a distance of d apart, and assume that X-rays are coming here, many different X-rays are coming here. So if I just take two X-rays coming here, the first X-ray hits this atom, the second X-ray hits this atom and reflects. So these are constructive interferences. So if the first wave and the second wave are traveling different distances, right? So by simple logic, I can say that the second wave is traveling SQ plus QT more than the first wave. Good with that? And if I know the angle of reflection, or angle of diffraction of the wave, can I not find what the extra path the wave is traveling? Simple trigonometry, 8th grade trigonometry, 6th, 7th grade trigonometry, you can do that. You can find out what SQ and QT are. You will see that SQ and QT is equal to 2 times d sine theta. This is d sine theta, that's d sine theta, right? So this is 2d sine theta, which means if I have 2 waves hitting a crystal at 2 different layers of atoms, I simply will say that the extra path length that the second ray will have to travel is 2 times the interplanar distance times the half of the angle of reflection or angle of diffraction, 2d sine theta. And then Bragg, Lawrence and William Bragg, simply said, I can equate that value to the wavelength of the wave, right, times a simple multiplier, which is how many orders of diffraction. Has it diffracted once, has it diffracted twice, has it diffracted 3 times, just an order of refraction. So it makes it so simple. N times lambda is 2 times d sine theta. Now, this is so very powerful that you can find d if you know lambda, which is the wavelength of the X-ray. You will know the wavelength of the X-ray, right? And you can measure the angle of diffraction. You can find d. So, if you do X-ray diffraction, you plot what is in your x-axis. What will you do in your x-axis in any X-ray diffraction curve? Any of you have done it? What is that? 2 theta, right? You do 2 theta, 2 times the angle of diffraction, and then you have the peak intensity of all the. Have you heard of d-spacing? So actually, if you want to do more nicer science, people use what's called a d-spacing in crystals. That is nothing but the d-spacing. So you're either representing the intensity as a function of theta or intensity as a function of your d-spacing. That's all you do. And then based on what you know about the crystal, you go back and infer what that crystal is. And then you can find based on lattice structure, you can do all of that. So this is a typical X-ray refractogram for a clean material. And again, I don't know if you know about Miller indices of crystals, 110, all that, but don't worry about that. In cement science, it's not all that important. But basically, you put a sample, X-ray beam comes in, you keep rotating the sample. Theoretically, you can rotate it to 360 degrees, but that doesn't make sense because if you have a homogeneous sample, anything more than 90, you're wasting time, right? So you can go from 0 to 90, and then typically, you know it takes a lot of time if you have to really do it slow so that you can get really nice signals. Sometimes 0 to 90 takes a day to do this X-ray. Others also will have to use it, so they may not give you the X-ray machine for a complete day. So you have to do it faster. If you have to do it faster, your X-ray will be noisy, but you can still find out what the peaks are and the software will help you clean it up. So it depends on what is the rate at which you rotate. And if you rotate from 0 to 2 theta. So if you know something about your structure, you will see in papers, we did an X-ray diffraction from 5 to 30 degrees. Or somebody will say 5 to 60 degrees, 20 to 70 degrees. Because you know what you're typically looking for, right? Now, these are not things, again, this is what I tell my students all the time. Any sophisticated experimental tool is not like going to fish market. I go to the market and decide what fish I want. No. I see a lot of fish and then I go scratch my head there and seeing which fish I want. You have to know which fish are you looking for. Okay? You may not have seen the fish, but you know I am looking for that fish. And then you ask the guy, I know this brand of fish you have. I don't know how it looks like. Can you give it to me? That is what this instrument does it to you. Garbage in, garbage out. Any sophisticated instrument tool. Just because I have an SEM, you take pictures, you will be I told you yesterday, you will be a nice photographer. Just because I have an XRD, I go and put some powders in it, you will be somebody with all these nice spikes, and you'll have to, I had a professor, an Indian professor, who was from Tamil Nadu, a friend. He says, now we have to take it to the astrologer to find what this is, right? Because if you don't know, you have no clue what this is. and you really did it without knowing anything, like now you have to go to an astrologer to find what these peaks are. But you have to know what you're putting in. And good research is all about hypothesis, right? You have to have a hypothesis. You could be wrong, and that's totally fine. But you have to have a hypothesis. I believe this is what is forming when I react this with that. I confirm or disprove my hypothesis. You cannot say, I mixed A and B and God tell me what I have. That is not research. That is what see, research is science. Science is not faith. I tell this all the time. You can have faith and belief. Okay? God controls my life. Perfectly fine to have that belief. God does not control your research. He has other better things to do. Okay? Faith is okay in life. Faith is absolutely bad in research. I believe I am right. What does that even mean? I believe I am right. It's only my belief. You can believe that I'm wrong, right? Science is facts. Facts have no. That's why, if you hear social scientists, politicians, literature classes. So, a lot of my students will take some advanced literature class, and they have to do some literature classes in undergraduate. They'll take literature classes as an easy class. You know why? You're asked to read Shakespeare, and you have to come and discuss. Shakespeare is not alive to come and tell you, no, that's not what I thought, right? You tell your teacher, this is my point of view. This is what I interpret. Can somebody say no? This is what I think Shakespeare told. Nobody can say no, right?